Okay, welcome back to 719 Mathematical Economics. So this is our fourth lecture. And today we're going to look at the linear systems and how to linearize the nonlinear systems. Okay, so let me give you a quick review of what we have done so far in this semester. So we started our journey with nonlinear programming. Okay, under this we solved problem like that. Okay, we solved problems like this, right? X subject to this and this. So then we started working on dynamical systems in continuous time. And last week we looked at nonlinear systems like this. And today we're going to look at systems like this. Okay? And at some point we're going to learn how to go from the nonlinear system to the linearized system, and then we're going to also learn how to go from this linear system to its homogeneous counterpart by normalizing. That's not entirely correct. By normalizing this system. Okay, so this is what we're going to do today, and next week we're going to start studying dynamic optimization in continuous time. In other words, we're going to study optimal control theory. Okay, so that's our plan, and then of course we're going to continue with other topics. Okay, so let's look at a linear dynamical system in continuous time. So once again, we have time. Time is a part of history. History is a part of the real line, and we have variables that change in time. So when I write xt, what I mean is x1t, x2t, dot dot dot, xnt, right? So xt in general is a vector, and then I write this, where A is some n by n matrix, B is some n by 1 vector. Okay, now of course Aij are real numbers, and Bi's are real numbers. Okay, so if you see a linear system like this, obviously one thing you're going to ask again is the existence of a steady state, right? So now, of course, the definition is the same. We want to do this, right? So, but be careful, this is a vector, right? So if we impose this condition, then we have a x star plus b equals 0. Right? Now be careful with the dimensions here. This is m by n. This is m by 1. this is m by 1, so this is m by 1, so this itself is the null vector. Okay? Now, obviously, this is a linear system of equations, right? So this is a linear system of equations. If you write this explicitly, you have something like this, right? A11, x1 star, A12, x2 star, dot, 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 A1n, xn star, plus b equals 0. So b1 equals 0. Then you have A21, x1 star, plus A22, x2 star, A2n, xn star, plus b2 equals 0. And this goes on until you have this, right? You have that. So the solution of such a linear system of equations could be found in this way. You have this, right? Then, of course, to have a solution, you multiply this with the inverse of matrix A. Okay? So if this inverse exists, right? If this inverse exists, this becomes the identity vector. So you have your steady state. Okay? And how do you know such a steady state exists? Well, if this inverse exists, it is unique, right? If such an inverse exists, it is unique, so you can find the steady state. Okay. Then one thing you can do with this system is this. Now, if you imagine the geography of it, so let's look at an example when n is 2. All right. So you have, let's say, x dot t equals 5xt plus 2yt plus 5, and you have yt equals minus xt plus 4yt minus 10. Okay, so obviously here your A matrix is 5, 3, minus 1, and 4, and your B vector is 5, minus 10. Okay? Now, if you think about the geography of it, what do you have? Well, these are two lines, right? So this is x, let's say, and this is y. Now, you want to imagine what x dot 0 curve is. So you have 5x plus 3y minus 5 equals 0. Put differently, you have 5 minus 5x divided by 3. So this is a negatively sloped line, something like, let's say, this. All right, so this becomes your x dot curve. And the other one would be what? The other one would be y dot equals 0. So you have minus x plus 4y minus 10 equals 0. So you have y equals 10 plus x divided by 4. So you can write this as, you can draw it as like, okay. So if I do it correctly, so the intercept here is 5 divided by 3. The intercept here is 10 divided by 4. So you have something like that, right? So this becomes y dot, and of course the solution seems to be appear around here. Okay, a steady state. So if
Hocam x'i galiba yanlış yaptık ama.
hangisini?
5x 3y artı 5 olması lazım. Siz eksi yaptınız. O da eksi olacak. Ya galiba değişecek. Ama bir şey değiştirmiyor galiba.
You mean this one? So this is I write. Okay, so this one is positive. All right. Yeah, you are right. So then I have this is minus. So let me do the entire thing from the very beginning. I mean, it doesn't make a big difference. So I already conveyed what I want to share, but let's do it correctly. So if the system is 5x plus 3y plus 5, then we have y equals minus 5 minus 5x divided by 3. So, oops. So if this is x, this is y, I have something like this, right? And then for the other, I had something like that, right? So this is x dot, this is y dot, and obviously you find the steady state here. Now realize one thing. Here, your A matrix has an inverse, right? How do I know that this matrix has an inverse? What guarantees the existence of this inverse? How can you take the inverse of a square matrix? What is the necessary condition?
Determinantının sıfırdan farklı olması mıydı hocam?
Yes, but the thing is that you have to speak in English, all of you. So that's a must. All right, that lecture is recorded. So I want you to require speak in English. Okay, so that's correct. The determinant of this matrix must be different than 0. So if you look at the determinant of this matrix, either I use this or this for the determinant, okay? So the determinant of A is equal to 5 times 4 minus 1 times 3. So it is 20 plus 3, it's 23. So it is different than 0. In other words, these two lines are linearly independent, right? These two vectors, what are the vectors? 5, 3 is one vector, okay? And the other vector is minus 1, 4. These two vectors are linearly independent. Okay? Because of linear independence, the determinant is different than 0, and then the inverse exists. Thanks to the existence of the inverse, you can find the steady state. Okay. Now, the thing is that for simplicity of stability analysis, we want to normalize such systems. Okay? Normalization. Normalization to do what? To make 0, 0, 0 the steady state. Okay, what do I mean? So let's look at the example again. Let's write another 2 by 2 system. Let's say x dot t is equal to minus xt plus 4yt minus 16, and y dot t equals 4xt plus yt plus 0. Okay? So suppose that is your system. Now, first, of course, check the inverse of the matrix. So your matrix is -1, 4, 4, 1. So the determinant of this matrix is what? -1, -16, -17. So it is different than 0, right? Then you have the inverse. So there is a solution there. There's a steady state. Now, if you draw this, so one of the equations is what? So x dot equals 0 is minus x plus 4y minus 16 equals 0. So y equals 16 plus x divided by 4, right? So you have something like that. This is your x dot equals 0. And then for y dot, you have minus, so y equals minus 4x, right? So you have, in that case, something like this. Okay, so that's y dot. So there is now, as you see, a steady state there, right? Now, by normalizing the system, we carry the system steady state to here. Okay? To show you another example, suppose that this is your system. Let's say this is x dot equals 0. And let's say this is y dot equals 0. Now, there's a steady state there, right? Now, you want to carry the system without changing the slopes to this point. Okay? You want to carry the system to this point by normalizing it. Okay? So how do we do that? How do we do that? Well, we're going to do this. So let's say our system is that, right? So a steady state is defined in this way. So x star is a inverse times minus beta, sorry, minus b, right? So I want to define a new variable, let's say z, okay? I want to define this new variable z as the deviation from the steady state. Okay? So z is a new variable I define, okay? And I define this variable as the deviation of x from its steady state value. Okay? Now this implies z dot t equals x dot t plus 0, right? Because this is dx star dt and it is equal to 0, right? So if z dot t is equal to x dot, I have z dot t equals a xt plus b, right? But I know what xt is, right? Xt is simply zt plus x star, right? You see what's happening? Well, if If this is true, I have AZT plus AX star plus B, right? So Z dot T equals AZT. As you see, the slope is the same, but this part is equal to 0 by the definition of the steady state. Okay? So if I give you a linear system like this, you can easily convert this system into a normalized system where the dynamics are the same, but steady state is at 0. Okay? The dynamics are the same, but the steady state is at 0. Okay? So that's the idea of normalization. So let's take an example. So let's write another nonlinear system. Let's say 3x minus yt plus 5. And let's say I have yt xt plus 4yt minus 6. Okay. Now, how do you normalize this system? First, you have to take the steady state, right? You're gonna find the steady state. So you basically have two equations and two unknowns, right? 3x star minus y star equals 5. X star plus 4y star equals, so this is minus 5, this is 6. Okay? Now, obviously, there's a solution there, right? It's a real solution. Now, if you know these solutions, you can directly write this linearized system in this way. So you define x tilde as the normalized variable. You define y tilde, sorry, that's not correct. Okay. You define x tilde t as xt minus x star. You define y tilde t as yt minus y star. Then your normalized system is this. X tilde dot t equals 3 x tilde t minus y tilde t, and y tilde t dot equals xt tilde plus 4 yt tilde. Okay? Again, your zt in the previous example is now x tilde t, y tilde t. Okay? So that's it. That's very simple. Normalization is very simple. And it is very useful because now in all our systems, in any system in this form, okay, in any system in this form after normalization, you have this, and the steady state here is 0. Okay, that's the beautiful part about normalization. And so this is just a technical thing, but from an economic point of view, most of the time we are interested in deviations from steady state. If you are familiar with impulse response functions, okay, there is something called impulse response functions. Okay, so if you have, for instance, a VAR system, okay, a VAR system is something like this, and there are some shocks here, okay, epsilon. So you may want to analyze the effect of one of these epsilons to x, and you see graphs like that. I mean, for instance, you see something like this, okay? And then, of course, there's a confidence band around that estimate. Now, this is usually taken as 0. So usually, initially, we assume that we are at the steady state, then the shock hits the economy, all right? So initially, we are at the steady state, then the shock hits the economy at period 0, then of course, x1, x2, dot, 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 in time changes. So this change is always measured relative to the steady state, okay? So especially in macro literature, macro models, we make such normalization. So it is not just purely a technical or simplifying issue, but most of the time we normalize our systems to the steady state. So when I observe a positive or negative value for a particular z variable, then I know that this is relative to the steady state. Let me give you another motivation for this. For instance, you are studying a macro model again, and in your model, let's say you have trend GDP, okay? So let's say this is the natural level growing in time, okay? You may have something like, for instance, this, right? So it exhibits growth. Then you also observe some fluctuations around that. So this is your Y actual, okay? So then if you imagine this as the balanced growth path or steady state, right? The deviation of YT actual from YT natural will give you a new variable that is sometimes called output gap. Okay. So, so such normalizations are very useful when you start modeling real economic systems. Okay. So that's one thing, right? So again, our roadmap is this. This is a nonlinear system. This is a linearized version of it. And then there is a normalized version. Now, I gave you this part. Okay? Now, in the next hour, I'm going to show you this. Okay? It's very simple. Nothing to worry about. But we're going to cover this, and at the end, we're going to have some discussion of stability issues. Okay? So let me stop here for your questions. We have around 6 minutes for your questions and comments. I want to start the discussion of linearization in the next hour. So I'm going to stop there.
Can I ask a question?
Of course, go ahead.
Can you explain once more the logic of the normalization?
Okay.
I mean, why we are doing that?
Okay. We are doing that for two reasons, basically. First, there is this technical issue. I want to get rid of this B term, right? I want to create a homogeneous system. Why I'm creating that homogeneous system? Because the analysis of stability is easier in this way. Okay? The analysis of stability is easier in this way, and it is, you know, much simpler, much intuitive to normalize all the systems so that their steady state is at 0. Okay, so that's the mathematical technical reason. The economic reason is that most of the time we are interested in an equilibrium state of the economy, let's say the steady state, and if a shock hits the economy or a policy changes, then I want to compare that relative to that steady state, relative to that reference point. Okay, so that reference point is usually the steady state or the balanced growth path, as I just showed you. So I want to see the deviation from that. By normalizing the system, I can directly do this, right? If I observe ZT, I know that what is the deviation of this particular variable, let's say inflation, from its steady state value. And usually the steady state value is taken as, for instance, the inflation target. Okay? So in most economic models, perhaps in all economic models, you see that type of steady state or balanced growth path that you take as a reference point, so that modeling directly the deviations from that steady state or that equilibrium point would simplify your analysis, would make it much more intuitive. Because when I observe 3%, let's say, in this impulse response function, if I observe at the third quarter, let's say 3.2% positive, then I say relative to the steady state value, the variable x, whatever variable that is, for instance, investment rate, is relative to the benchmark, it is 3% higher. Okay, so there are both technical reasons and more intuitive or economic reasons.
Okay, thank you.
And as you see, it's very simple because the slopes remain the same. We are just picking these two lines from the steady state point and carry that steady state point to the origin. That's the entire idea. Okay, any other thing?
May I ask a question?
Of course, go ahead. I mean, guys, you don't have to ask for permission. Just go ahead.
Can we repeat, please? How did we define ZT?
Yes. So it's very simple. It is defined as the deviation from the steady state. Let me just show you. It is defined here as the deviation from the steady state, right here. This one. Okay. When we have that, and if I take the derivative, I have z dot equals x dot. Why? Because x star is fixed, right? This is fixed.
Yes.
Then I got x dot from this. Okay. Right?
Yes.
Here. Then I replace xt with this, right? Because this implies xt equals zt plus x star.
All right, thank you so much.
And then this becomes 0, and you have that. Okay, and that's not true for just 2x2 systems. That's true for any system. Okay, and any linear system. Okay. Now my time is almost 1:40. This record will take around 15 minutes, so let's meet at 1:55, if that's okay for everybody. At 1:55, we're going to continue with the linearization of nonlinear dynamical systems in continuous time. Okay?
See you.
All right, bye-bye.